So I'm going to cover now the topic of optical diagnostics, which you remember is to exploit the effects of cells or tissues on light. So the principle is that we have some source of light, we have the tissue with some structure, some biochemistry, some metabolism, and we're going to let the light interact with the tissue, and by having detector outside the tissue, maybe also inside for some applications, we're going to measure some difference in the light signal here compared with the input light. And that difference may be a difference of intensity, a difference of the spectrum, a difference in the polarization. So some measurable property of the light is changed because of the interaction with the cells and with the tissue. And so by measuring the change, we're able to understand something about what's happening in the tissue, either structural or biochemical or metabolic, functional. And I showed you this scheme earlier, just in the reflection mode, but remember this could be transmission also, that generally for light, photons go into the tissue, they're multiply scattered, which is why you see let me just put the light there for a second, why you see the scattering of light in the tissue. And so some of that light is reflected diffusely, or maybe transmitted diffusely. Some of it is absorbed and then re-emitted at a longer wavelength as fluorescence. Some of it interacts with the molecule but is not absorbed but has a change of wavelength, and that's known as a Raman. And of course this can have differences in polarization, differences in phase, and so on. There's a specular component about a small percentage of the light comes from the surface, which is usually not important for the surface, but you can also have specular reflection from structures inside the tissue, which is important. So this specular reflection, for instance, is why Professor Bagnato's head, you can see the light. Thank you for the demonstration. No, I won't point at my head.
I have one question.
Yeah.
You put a Raman scattering
Yes.
inside, and we know that Raman is a second order effect.
Yes.
And I thought that the most contribution comes from the first few layers and less from the bottom, while the fluorescence comes from a whole bulk. Is that
No, that's a little distorted. I mean, just to give you an idea, if we put ballpark, typical, if we put 1 million photons in of, say, visible light, so if I take this laser and I have 1 million photons coming in here, about 999,000 photons are diffusely scattered. About 1,000 photons come out as fluorescence, and about 1 photon comes out as Raman. So this is the strongest signal. I mean, this looks, again, let me put the light out. You know, the color here from my finger is the same as the beam. So you know that this is elastically scattered, is scattered without loss of energy because it does not change wavelength. The fluorescence is about 1,000 times less intense, so you need to put a filter in to eliminate this red light so you can see the weak fluorescence. And to measure the Raman, you need to use special technology, which is very, very sensitive, and you have to eliminate this and you have to eliminate this. And we'll see how that's done. Okay, so I just want, this is on diagnostics. I'm going to show you examples from cancer and non-cancer, but just to give you a little motivation, here is the survival rates for cancer. of different types of cancer. And I'm sorry that we've lost the writing on here.
Not in the.
I know, I've actually forgotten what the scale is here. Let me, why have I lost the writing? Because, there we go. I've done, I was playing around with the fonts. So this is the survival if the tumor is local when it is detected. Here is the survival if it's spread but is still regional, and here if you have metastasis. So you see what we all know, early detection is very important. Okay, so if you can detect cancer while it's still at this localized stage, before it started to spread in the tissue, before it started to go to other organs, then the survival is much greater. So there's tremendous importance in early detection of the disease. And that's just one example from cancer. So early detection is critical. This is just a summary in which we think of diagnostic usually as detection of disease. So does the patient have a cancer, or does the patient have Alzheimer's, whatever. But in fact, diagnostics is a more general term here. It can be used, as I talked this morning, to predict risk of the disease, like the breast cancer risk. Early detection or differential diagnosis, in other words, detect the tumor, but also make sure that it is a tumor. Staging, is this an early stage, a later stage tumor? Detecting of the spread of the disease, or is the disease progressing? Local, so that's all to do with finding out, does the disease exist? Where is it? And so on. And then once you start to get into, okay, you have a cancer somewhere, now you want to start treating it. If you're going to do a targeted treatment, you have to localize accurately where it is. If it's in the lung or the GI tract, you want to know exactly where, so you can target the treatment. You can use it to guide the therapy, like we saw this morning with the surgery, with the fluorescent surgery. Use it to monitor drugs or to detect the drugs. And also, very important, is to use these techniques to follow up after treatment. Is the response being good? Does the disease recur? What other changes have happened? Are there damage to normal tissue? And so on. So you should be broad-minded about diagnosis and not just think, well, diagnosis is detecting the tumor. And then, as I've listed here, there are various classes of signal, the absorption, the elastic scattering, fluorescence, inelastic scattering, Raman. And then there are a number of techniques that are diagnostic techniques in this sense that use light, but they use the detection is not the detection of light itself. In the case of photoacoustic techniques, the light goes into the tissue as a pulse and is then used to create an ultrasound signal from the tissue. Because if you have local absorption, you have local heating, rapid heating, you get expansion, and that produces an ultrasound signal. So it's a photoacoustic technique. Similarly, you can have the light absorbed locally and producing heating, and you detect the temperature. So there's some techniques that are dependent on other technologies for the detection, such as sound or heat, but where the signal is generated by the absorption of light. I don't really have time to go into these. If people are interested, we can talk about it maybe tomorrow. And in general, for each of these techniques, you can do point spectroscopy. In other words, you make the measurement at a single point. That's often called optical biopsy, although that's not quite right, because a biopsy is where you take the tissue, and here we're trying to not take the tissue. So this should really be called optical biopsy not. But nobody likes to use such an ugly term. And this is our imaging, and this can be a one wavelength or many wavelengths. So let me start. I'm going to show you a whole series of techniques, and maybe this is all I'll do today, since I'm sure you're fed up listening to me today. I'll just talk today about techniques that are based on absorption and elastic scattering. And then tomorrow we'll talk about fluorescence, Raman, etc. Okay, let's look a little more detail about what happens when the light goes into the tissue. So here we have, again, the light that's going into my finger is multiply scattered, and you have a diffuse signal coming out. So this are some simulations, computer simulations, by a technique known as Monte Carlo. Anyone is familiar to anyone? Okay, so it comes from Monte Carlo, from gambling. The casino, yeah. It's named after the casino because you calculate the path of individual photons in the tissue and whether or not there's a scatter at this point is determined by the roll of a dice in the computer. So the computer rolls a dice and it says scatter or absorb. Scatter or absorb. And that's why it's called Monte Carlo. Technique originally developed for particle physics, actually, which is my original field. So I did Monte Carlo when I was a graduate student, but for a completely different purpose. We actually did the, it's funny how your background influenced, we actually did the first paper on Monte Carlo simulations of light in tissue. It's a paper written in 1983, and it's completely wrong. Okay, not the principle, but the numbers that we used for the properties are just stupid now, but we didn't know at the time.
Do you know what's the probability of having ballistic photons per unit of length of tissue?
So the probability that the photon will go straight through the tissue, typically in the visible, it's about 10 to the minus, let me get a number, 10 to the minus 2 or 10 to the minus 3 per centimeter. So it's pretty small. Anyway, so you can watch these photons going through, and of course, as well as scattering, at any point the photon may be absorbed. Okay, so at some point the photon will just disappear. And so if we had a detector here, or here, doesn't matter, and you measure some signal, then the signal relative to the amount of light that you put in will depend on the absorption and the scattering. So if we have a detector here, and we have going from here to here to here, we have less scatter or more absorption, then the pattern will change and the signal will change. So think about why that is. For instance, if we compare, if we said this was low absorption and this is high absorption, you notice what happens is that you mainly eliminate the very long photons because the probability of being absorbed is higher. Okay? So you tend to confine the beam of detected light because of high absorption. And similarly, if the scattering is lower, then the chances of a photon wandering away out here is less. So this signal, both the intensity relative to the input and also its distribution in space, is dependent on the absorption and the scattering properties. So in this way, you can measure this signal and say something about not about the scattering in here and also about the absorption. And then, of course, if you do this at different wavelengths, you can know things about the absorption spectrum or the scattering spectrum. So this is a non-invasive way of telling us about the absorption and scattering in the tissue.
Just to clarify, you are just showing those photons that eventually reach the detector.
These are the detected photons. There is light everywhere. Right? But you don't care. You're right. Yeah, this is the signal that we must. This is our diagnostic signal. And it's not that the light is bending, right? There's light going the individual photons know nothing about the presence of this detector. Right? This is not a magnet. So the individual photons just do their own thing, but of course, for a photon to reach there, there's a certain probability of a path through the tissue. So, if we were to make such a measurement, then the intensity here will be different if the absorption is different. And therefore, because we know that the absorption of different components in the tissue depends on the wavelength, so we think we would be able then to make some estimates of these different absorbers. So you might be able to say, if you know the spectrum of hemoglobin, could you measure the amount of hemoglobin by measuring the spectrum of the light that comes out here? And I'll show you the answer to that is yes. Okay, and this is just, I showed you this before, is illustrating the fact that there is this wavelength dependence on this, of this diffuse distribution of light. You'll notice that I wanted to make a point about these absorption spectra. So these are absorption spectra for specific molecules. So that if we look, for instance, what is the most boring molecule here? People in the US would say, where's the Canadian? Okay, the most boring molecule is melanin, because America thinks that the Canadians are boring, you see. And so melanin is the most boring. It just decreases with wavelength, very little structure. Bilirubin, I showed you a couple of days ago for therapy, has a nice peak in the blue. These are various nucleic acids. This is in the ultraviolet part of the spectrum. Water we saw was like this. Fat has a different absorption spectrum from water. In fact, there was 10 years ago a device, an optical device for measuring body fat by looking at this signature. And here's hemoglobin, blood, which I'll return to several times. But let me point out the fact that this is hemoglobin, this is oxyhemoglobin. So changing the oxygen status of hemoglobin makes a big difference to the spectrum in the visible part. And that's very important for some medical applications. So the absorption basically is simple in the sense that it's due to specific molecules. What about the scattering? Why are we getting this light scattered within the tissue? That's a little less specific in that the elastic scattering is due to microheterogeneities in the tissue refractive index. So what does that mean? You know from school that if you took the old experiment where you had a block of glass and you had a light beam come in, what happens? The rays are bent, and what happens here? Bent back again. Mm-hmm. So this is why if you go fishing, the fish always looks at a different position. So if you put your hand in to grab the fish, you always miss. All right? Because you think the fish is sitting here, whereas the fish is sitting here. So this refractive index basically tells you how much light is bent. And of course in cells, you have membranes, you have the nucleus, you have mitochondria, lysosomes, etc. This is going from lipids to water, etc., which have a different refractive index. So there's lots of micro bending within the cell. The question is, what's the main contributor to scattering in the cells? And if you look at the size of the objects within cells, so we have cells about 10 microns, nuclei, maybe a few microns, mitochondria, about 1 micron, lysosomes, vesicles, tenth of a micron, individual membranes, 1/100th of a micron. So all of these are have a different ratio to the wavelength of the light. So if we take green light, for example, which is half a micron, that means that green light, the wavelength of green light is about the size of these structures, is much less than the size of cells, and is much greater than the size of individual membranes. And red light is a bit more towards here. And it turns out that the ratio of the wavelength of the light to the size of the particle is a big factor in how large the scattering is, both how intense is the scattering, but also what's the direction of the scattering. So why is the sky blue? I mean, the sun is not blue, right? The sun's not giving out blue light. So why is the sky blue?
It's giving sun.
It's giving sun, yeah, right.
Not only.
So the sky is blue because blue light, the sky is not full of cells. So, the sky is full of molecules, or tiny particulate matter, which are the size of which is relatively small compared with the wavelength. And in that situation, the scattering process is called Rayleigh scattering, where the wavelength is large compared to the scattering particle size. And the sky is blue essentially because the blue light is bent more than the red. And so the sun is here, here's the surface of the Earth, you're standing here, and the red light tends not to be bent so much as the blue light. So you see the blue light. And that is the same in cells. If the size of the particles are similar to the wavelength, then you have a process called Mie scattering. And the point about this is that these have a very different wavelength dependence. So the Rayleigh scattering, the probability is proportional to 1 over the 4th power of the wavelength. So very, very strong wavelength dependence, which is actually why the sky is so blue. Whereas with Mie scattering, if you're taking larger particle sizes, the probability of scatter is more like a 1 over lambda dependence. In addition to that, Rayleigh scattering, if you have a very small particle and light comes in, the scattering tends to be the same everywhere. It's called isotropic. Whereas with Mie scattering, if we have a cell with shorter wavelength, when you get scatter, it tends to be in the forward direction. So there's a difference in the probability and in the distribution. And it's thought that most of in the visible part of the spectrum, most of the scattering from cells comes from the mitochondria, with the individual mitochondria as an object, mainly being Mie scattering, and the individual cristae within the mitochondria mainly being Rayleigh scattering. This is important because it makes a difference to how the light is distributed in angle when the scattering takes place. And just in very general terms, in the visible and infrared part of the spectrum, most tissues are very highly forward scattered. Now I say that, and then you say, well, that's not true, because you just showed me that you can see light coming outside. So if the light is forward scattered, why is there not just a beam going up there? And of course the reason is that individual scattering events are forwards, but there's thousands of scattering events. Okay? So that the average effect is to give more like a uniform pattern of scattering. Mm-hmm. So don't be confused when people talk about the forward scattering nature of tissue. That's at the level of the individual interactions. But when you take the result in bulk, there are so many interactions that the scattering looks isotropic. The photons entering my little finger here that you are seeing have probably scattered 100,000 times. So I want to give you some examples of applications of this interplay between the absorption and the scattering. And there are really two classes. One class of application is where you know the specific molecule that you're looking for. Might be hemoglobin, might be a drug, whatever, but you know what you're looking for. The second class of applications, which I'll do first, is where you don't know what you're looking for. You're not looking for a specific molecule. You're making some measurements of the absorption and scattering properties of the tissue as a whole and using that to make some diagnosis. So here's one example. This is a system that uses a white light source delivered into an optical fiber. I told you yesterday this is not very efficient, and that's true, but you can get enough light. Goes into the tissue, and here's a second optical fiber to a spectrometer, a detector, and a computer. So this is a very simple optical biopsy system. And you could take that optical fiber and put it anywhere in your mouth, up your nose, on your hand, wherever. And this is examples of measurements in, this is in bladder. In the bladder, so this is actually done through a cystoscope. So the fiber is put through the cystoscope, and you see the spectral. This is the diffuse reflection spectrum, so the light's going in and then it's coming back out. And you see that this is in the ultraviolet part here, and then you see it's fairly flat, and then increases a lot above 600. And this increase here is due to the fact that the absorption by blood is falling rapidly in this region. And the group that did this study made the observation that if you try to use a simple device like this for diagnostics, so let's say that you had a patient who might have suspected bladder cancer, but you couldn't see anything, you go in with the cystoscope and you make measurements at multiple points on the bladder. They were able to show that there are significant differences in the reflection spectrum between the normal sites and the sites of cancer. And a little surprisingly, this was not expected, they found the biggest change was actually to the slope of this part of the ultraviolet spectrum. So if you measured this part of the spectrum, that had the biggest difference. The slope there had the biggest difference between normal and diseased. So you could, in principle, make a simpler device in which you'd say just measured at this wavelength and measured at this wavelength and take the ratio. And if that ratio is large, then it would be a signature for cancer. If it was small, then it would be normal. And what was found, of course, is that different organs have different characteristic signatures, so you would need a different algorithm for detection for cancer in different sites. But it's a very nice example of a very simple reflectance-based optical biopsy, very cheap. You could use a white LED nowadays, very simple photodiode array, or even single detector with 2 filters, and just make a device. So there's several groups are doing clinical studies with that sort of technology. I wanted to show you the endoscopy. Endoscopy is very important in cancer because, and let me just let this film run. So this is a endoscopic procedure in the esophagus. So this patient has Barrett's disease. I talked about that yesterday. It has these regions of transformed mucosa. Now, this is non-optical biopsy, or optical not biopsy. And in patients with Barrett's disease, and with this condition, every 6 months or every year, they have every centimeter, you take 4 biopsies. So this is pick, 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 right? And those biopsies go off to the pathologist. And if the pathologist finds that one of those biopsies is dysplastic, as we talked yesterday, your esophagus comes out. Or you get PDT, maybe. So this is a pretty, so for Barrett's, it's a difficult procedure, but in general, although endoscopy is very commonly used, it's relatively non-specific. You know, you're dependent on the experience of the endoscopist to really see very subtle changes in the tissue. I mean, if there's a big lump there, it's easy, but that's not the clinical problem. And it's not generally thought about why is endoscopy so important, and the reason is that for cancer, if you remove skin, about 80% of solid tumors start as very thin lesions on the lining of hollow organs. Very few tumors arise in the middle of a mass of tissue. You know, sarcoma, prostate, but that's relatively few compared with the lung, the GI tract, the bladder, the cervix, etc. And that's because those surfaces are turning over rapidly. They have to turn over rapidly because they're losing the cells all the time. And of course, those surfaces are what's exposed to all the carcinogens. So when you have a McDonald's, you know, or when you smoke, or when you drink, all the pleasures of life are an insult to the lining of our hollow organs. So it would be much better if we didn't have any hollow organs, but it's hard to design an animal based on that principle. So endoscopy is very important. So a lot of the development of optical diagnostics is based around endoscopy because this is an optical technique. Conventional endoscopy, the movie that you just saw is an image of diffusely reflected light. And when the endoscopist is looking here, he's looking for changes in, for example, the color of the tissue, and that is exactly the same. The endoscopist with his eye is doing what you're doing here, okay? But just in the visible range. So a lot of the effort is to do with helping the endoscopist see more. Okay. So this is a couple of examples. What about examples based on specific signatures? In other words, you know the molecule that you're interested in. Well, we showed in the case of bilirubinemia, the bilirubin accumulation in premature babies, that you could destroy the bilirubin with blue light, but you can also use blue light to detect the circulating bilirubin. So this was a very simple handheld bilirubin monitor, which you just put a little probe on the baby's skin somewhere, and you look for this signature, and you monitor that, and it tells you with the treatment is the bilirubin going down. All right. It's a simple signature because you're looking for a very specific condition, and there's a very specific optical spectrum. What about the oxygen? Well, here again is an example of a very simple device, and I'm going to show you now a few examples of oxygen monitoring, or hemoglobin based. So again, we have a light source, optical fiber, detector, and spectrometer. So one example of a very simple measurement, but which actually clinically was very useful. This was a patient who had femoral artery. So the main artery in the leg was blocked and required to be basically reconstructed. So by grafting in another piece of normal artery. So the surgeon goes in, and of course the problem is that there's no oxygen getting to the bottom lower leg. So the surgeon goes in, does the repair, finishes. And the question is, did he succeed? Right? Has the surgeon succeeded in getting blood flowing to the lower leg? Now, you could wait and see whether or not the leg recovers function, etc. But if you want to know the answer immediately in the surgery before you sew up, so that if it has not worked, you can do better, you could do this by putting this probe onto the lower leg. And this is the signature you get. So here is the signature. This is it. This is the signature just before the blood is allowed to flow back. So there's a clamp, and just before it's allowed to flow back. Now, you'll notice it's a little hard to see here, but if you look at the hemoglobin spectrum here, that is without the oxygen, you see that there's one peak in this part of the spectrum. So it's a single peak. If I draw it here. So at that part of the spectrum, the hemoglobin signature looks like that, and the oxyhemoglobin signature has two peaks. Very characteristic. And it's to do with the fact that when the oxygen goes onto the molecule, it changes the structure. So we can look for this characteristic peak. So what happens? So the clamp is released, blood starts to flow, and here you see increasing flow. So what happens initially? This is 0 minutes, 1 minute, 2 minutes, 3 minutes after release. And here you see an increase in the hemoglobin signature, but it's still all deoxygenated. Okay. There is no double peak here. This indicates you have increased the flow of deoxyhemoglobin. And that's presumably because you're essentially clearing out all the deoxygenated blood that's already inside the leg. So there's quite a volume of blood in here, so you have to wash that out before you start to see the recovery of the oxygen signature. And here, very beautifully, is the peak, double peak, which is absolutely characteristic of oxyhemoglobin. You know for sure that this is oxygenated blood that's flowing back into the tissue. And then if you wait a while, in fact, this overreaches. You can get this actually, this excess supply of oxygen to the tissue can actually cause damage itself. So you have to be careful not to reoxygenate the tissue too quickly. It's called reperfusion injury. If you have a tissue that has very low oxygen and you suddenly increase the oxygen quickly, then that can actually injure the tissue. So you want to control this. This is actually not well controlled experiment or study here, but nevertheless. And then it settles down, and so the leg is fine. You can finish sewing up. So with very simple technology, you can make a big difference to a surgical procedure as a diagnostic. Another example, just to make it visible, you can use that same very simple technology if you're a dermatologist and you're interested in sunburn and tanning and so on. You know, we all look like this sometimes. Some of us look like this, at least the ladies look like this. Obviously, the diffuse reflection spectrum is different here from here. So here's the unexposed skin, here's the sunburn, and here's the tanning. And of course, you don't need a spectrometer to see this. You can monitor how this changes with time. So you get the sunburn happens. So you go to the beach and you lie out all day, and in the middle of the night, it's terrible. Right? So this takes some time. You don't instantly go red. Right? This takes some time, and then you know that it takes 2 or 3 days before it goes away. You don't instantly go brown. It takes some time for that process to happen. And so you can monitor that with such a spectrometer. And again, what you're seeing here is this part of the response, my battery is running out here, this part of the response is the increasing blood flow. Notice it's oxygenated. So this is the erythema response, quantified. And you can actually see there are changes in this infrared part of the curve which correspond to changes in the melanin. Remember the boring melanin spectrum? So you can detect that in this part. So this may appear to be rather trivial application, but in fact companies that produce sun protection lotions use this sort of technique to determine, not usually in people, usually in animals, to give an objective, quantifiable measure of the efficacy of the sun tanning protection. Here's a very important example, application. So here's a premature infant, and you definitely don't want to be born too early because your systems are not up and running. So there's various risks. You can have the bilirubinemia, but actually the greatest risk of premature infants born before full term, is transient, that is sudden loss of oxygen to the brain. So sudden loss of oxygen to the brain is the major cause for mental deficits in adulthood from premature infants. And so it's very important to be able to know when this happens. It happens very suddenly and for a short time, and usually is very, very easy to fix. What happens is that when the oxygen falls in the brain, the nurse rushes in and tips the baby's head up, down. See the baby, tip his head down for a few minutes, and it's fine. How does she know when to run in? Some people have tried to do this by putting premature infants inside magnetic resonance scanners. It's interesting, but it's not a practical solution. So the technique that's become standard for this is to use the fact that if the brain becomes deoxygenated and you put light in and you measure the light, and you can measure it through the head, through the whole head. The baby's head is small enough, you can get light through the whole head. You can look for the oxygen-deoxygen signature. Oh, thank you. Thanks very much. Is this a green one or a red one?
Yeah, it's a green one.
Oh, okay. Well, I'm going to go blind. Thanks. You can look for the signature. Now, in fact, in this case, because you still have to go through quite a lot of tissue, you cannot use this part of the spectrum because not enough light gets through. So you can't use this double peak here. So you have to look at the difference in this part of the spectrum. And you see the curves actually cross over. So it's quite feasible. So you look in this part of the spectrum where the curves cross over, and you measure at multiple wavelengths, essentially to sample the signal. And then you're looking at, well, is the signal at this wavelength smaller or larger than the signal at this wavelength, and so on, and you can sort that out. So this is typically done with a series of laser diodes. This is dying also.
No,
it's okay.
This is bad.
This recovers in pulse mode. So you have a series of laser diodes coupled into optical fibers. They go in here, and this is electronically controlled. So you just vary the select the wavelength, and you have detectors here, and you sample the signal. And now, of course, you can connect this to a computer, and you connect the computer to a bell. And so when the oxygen saturation falls, the bell goes bang, 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 bang. The nurse rushes in, tips the baby up. Okay, go back to reading the newspaper. Or helping other patients. So this is all. So this is a very standard technique. This is also being used during birth. Again, during birth, how many pediatricians here? No. No, okay. We have a wife of a pediatrician. Yeah, yeah, yeah. During birth, one of the clinical decisions is the baby getting into trouble if the birth is taking a long time. And the conventional way to monitor this is to, the obstetrician tries to reach in and maybe grab a finger and put a pulse oximeter on it, which is essentially the same type of technology. But you know, the baby could have peripheral blood, but still be losing blood in the brain. For instance, if there's a constriction to the neck, you know, the finger will be okay, but it's the brain that matters. And so there have been developments of this type of optical detection on the brain, and this is an example. This is the separates the oxygen and the hemoglobin and the oxyhemoglobin signature, and you can see that this is the time that the head is delivered. So at this point the head is delivered, and suddenly this baby is fine because the oxyhemoglobin goes way up. And if the baby is getting into trouble, then you may have to use a cesarean section. The biggest technical challenge in this is finding a way to make this stick to the baby's head. People have seen the movie Alien. In the movie Alien, you know, that's the technology that's needed, because this is difficult to access and is slimy and slippery. So how do you get an optode to stay there? Is actually quite a technical. It's a major technical challenge here. The optics is trivial. It's how you get this thing to stick to the baby's head. Use another example. Optical probing is now used in neurophysiological monitoring. So again, here's this guy. Looks a bit silly, but he's connected to a system that's delivering light on one fiber bundle and detecting it in another. So you're putting light in here and you're measuring here. The skin is intact, it's completely non-invasive, it's exactly the same as I'm doing now. But you do it as a function of wavelength, and you're looking for the hemoglobin, oxyhemoglobin signature. So this is an example. This is time in seconds here, so this is over a couple of minutes. And so this is measuring in the right motor cortex, so over the part of the brain that controls motion in the cortex. So here you see the light is going in and is basically sampling the brain. So it's sampling the cortex, looking for the hemoglobin, oxyhemoglobin signature. And this is a measure of how much the signal changes. So in this case, what happened was that the detectors are put on. I'm not sure where the motor cortex is. Where is the motor cortex? Is it here or here? Any anatomists? Anyway, wherever the motor cortex is. So the measurements are over the right motor cortex. And what happens here is that the subject was asked to tap their finger. In other words, the subject was asked to do a motion with the left hand, which of course requires energy expenditure in the right motor cortex. And that means that the right motor cortex needs to have more oxygen. So there's an increase in the oxygenated blood supply to the right motor cortex when you do that. And so you can detect that non-invasively by optical techniques. So it's kind of interesting. This is a hemoglobin, oxyhemoglobin-based signature. It's also been found that if you make these measurements on a very short time scale of say a millisecond, that you can also detect changes. And then that cannot be due to changes in blood supply because the vascular system does not respond that quickly, and is thought to be a scattering change due to the fact that when the cells are active, when the neurons are active, they shunt sodium and potassium across the cell membrane, and that changes the cytosol to interstitial fluid refractive index ratio. So you can actually detect the change in scattering due to the cumulative effect of all those cells that are being sampled on a millisecond time scale. So people are now using this sort of technology in combination with magnetic resonance and other imaging techniques. Obviously, this does not have tremendous spatial resolution, but it does have tremendous time resolution. And one example of that is here, where this is a patient with epilepsy, where this is a SPECT, a radionuclide scan, and here is the optical measurements. Again, this is not a surgical procedure. This is just to hold the optical fibers in place. There's nothing sticking into the skin here, and this is a patient who's having an epileptic seizure, and you're able to monitor the fact that an epileptic seizure means that part of the brain has a tremendous burst of metabolic activity, and that requires energy. You're required to produce more oxygen. So you can use this to monitor and try to understand the seizure process. These measurements here are made at different positions, and you'll notice that the signal is different, so there's some expectation that you might be able to use this to localize the focus of the seizure by a sort of projection technique.
Professor, here, can the light reduce the brain metabolism?
Not at these levels. I mean, this is the amount of light being used here is about the same as this pointer. This is just a few milliwatts of light. Again, on the subject of monitoring where you know what you're looking for, this is an example I showed this morning of the prostate treatment with this drug, 2CAD. And unfortunately, this drug is not fluorescent, so we cannot use fluorescence to monitor. So we use absorption spectroscopy. This is just an example of absorption spectroscopy in blood, where we're able to look for this characteristic signature of the molecule in blood, and you can then follow the pharmacokinetics in blood, but also it's possible to do this in tissue. And so in this case, what is done is that we use a white light source, and that delivers light into the prostate through the urethra. And we have detectors in the prostate for monitoring the light for PDT. And so we measure the spectrum in the tissue. So here's the spectrum before the drug is given, and then here is the spectrum immediately after the drug is given, this red curve, and here is the spectrum a few minutes later. In fact, this shows you that this drug, before it is injected and for some time after it's injected, has an aggregated component. So part of the molecules are actually sticking together, and this peak here is characteristic of the aggregated molecule, and then you see in vivo this drug then disaggregates because of the microenvironment and becomes this, and this is an active peak. So you can then measure this. This is a function of time. You can then measure the drug in this way as a function of time. So it's a way of doing non-invasive or minimally invasive in vivo pharmacokinetics of drugs. So people are looking at this. This is a PDT application, but people are looking at this for other therapeutic drugs. Can you monitor drugs in the body and their pharmacokinetics by, if they have a known signature, of some sort, and you may have to look in the infrared, for example, to find the signature, or maybe in the blue, wherever. If you can see that signature, you can then monitor the pharmacokinetics non-invasively instead of taking blood samples. Just measure. So that's of very general interest. So I just want to spend a few minutes now. You'll notice that all of the examples that I showed you really had no absolute numbers on the y-axis. So we're making measurements and we're looking for changes. You know, tap your finger, tip the head up or down. You're looking for changes, but it's very important if we were able to measure the absolute signal. And I'll give you an example of why that's important. If we look at the case of the baby in the head, and we have that baby connected to a monitor and the alarm goes off when the oxygen drops. Now, the problem is the oxygen may drop from 95% to 85%. And that's of no clinical significance. You can leave the baby to sleep. If the oxygen drops from 85 to 60%, you've got a big problem. You've got to do something. And so it's not really quite enough just to know that it's changed. You would really like to know the absolute difference, and even if possible, the absolute starting and finishing level. And here's the problem in doing that. If you do absorption spectroscopy in the chemistry lab, for example, you take a cuvette of an absorbing solution and you put light in one side and you measure the intensity transmitted, and by Beer's law you have a simple exponential relationship, and so you can get the absolute value of the absorption, say the oxyhemoglobin value, of this unknown absorption coefficient from taking the measurements of the transmitted versus the input light and dividing by the thickness of the sample. Pretty obvious. The problem is, if you have a scattering medium, you don't know the optical path length. Because in the case of the non-scattering, the optical path length, the distance traveled by the photons, is the same as the physical path length. But in the case of a scattering medium, the optical path length may be many times the actual physical path length. And you don't know that a priori. This means that quantitative spectroscopy is very difficult. And in imaging mode, it means that this scattered light will reduce the contrast and the resolution. So that's been a problem for a long time in biomedical optics. A number of possible solutions are available, and I just wanted to talk about one which is the best. So here, although the baby's head may be 10 centimeters across, the light might have to travel 50 centimeters on average. And therefore, you don't know the size of the cuvette, so you can't measure mu A. So you don't know the absolute value. You can only tell, is it going up or down? So one potential solution is to use another property of light, which is the fact that it has a finite velocity. So how long does it take for light to come from the sun to the earth?
5 minutes.
8 minutes.
Oh, that's pretty close. 8.5. 8.5 minutes for a photon produced in the surface of the sun to reach the earth. So the speed of light is not infinite. It's 20,000 in a vacuum. In space, it's 30 million centimeters per second. In tissue, because of a refractive index, the reason that the light bends in going through a piece of glass is that the photons slow down. So it's about a third less, so it's about 20,000 centimeters a second. That's a kind of a difficult unit to think about, so mostly we think in terms of how far does light go in a nanosecond. And light goes about 2 centimeters in a nanosecond. Actually, that's wrong. Fifth of a millimeter, what have I done wrong? 0.2 millimeters. Sorry, that should be 20 centimeters in a nanosecond. Or in a picosecond, it travels about a fifth of a millimeter. So that was academically interesting until about 15 years ago, when it became technologically possible to measure that in tissue. So what you do is you take a very sharp pulse of light, typically picoseconds in duration, and let's say we're measuring on the surface. So we have light going in here, and we're measuring here. So you put a picosecond pulse of light into the tissue here, and you measure the light as it comes out here. Now, obviously, for some time, there's going to be no light, because none of the photons have reached the detector. And then you start to see the light coming in, so the photons wander around, start to come out, and then, of course, they're coming out and they're being absorbed, and so they decay away. So in the mid to late 80s, it became technologically possible to do this using picosecond pulse lasers and very fast detectors. And this shows an example of a measurement. So here's the pulses. These are repeated pulses. And here's the light coming in, getting brighter and brighter, and then dying away. So you say, well, that's amusing. How can you use it? This just shows this in graphical form, pulses of light coming in and dying away. Here we have the source and detector, and here's a detector down here. So this is simulated. So there is a time, this is a movie. When you put a pulse of light into tissue, there's a movie of what happens to the light. It's not just instantly coming out. And so you can think, if you make a measurement, as this wave of light goes through, so you will pick up a certain curve for the time kinetics. These are often called banana functions because they're kind of shaped like a banana. Each photon is working completely independently. The photons do not know what the other photons are doing. Each photon is just wandering through, but there is some probability of the photon reaching here. So this banana function is sampling this volume of tissue. There's light going down here and so on, but that's a very small chance of getting to the detector. And here is the algebra of this. You can describe the shape of these curves, by this equation. And I don't want you to bother about this equation except to make 2 points. One is that this equation depends on the absorption and the scattering, as you would expect. But most importantly, it turns out if you look at the tail of this curve, and mathematically that means that we take the final slope on a logarithmic scale. So you take, for the mathematicians in the room, you take the asymptotic limit of the first differential of the logarithm of reflection. For the rest of us, that means, what's the slope? Amazingly, and this was discovered in 1988, the final slope does not depend on the scattering. It only depends on the absorption. This is a very surprising result. I first heard this in a room at University of Pennsylvania, and I was sitting next to a colleague, and we turned to each other and we said, that can't be right. That's far too simple. How could that possibly be? That it only depends on the absorption. But it turns out it's true. It does only depend on the absorption. And
can you repeat?
So you take these time curves on a log scale, and it turns out that the final slope of these time curves, so if we look back here, this final slope on a log scale only depends on the absorption. You have to think quite hard to come up with a physical explanation of that, in a so-called hand-waving way, it's because out here, each photon has been scattered hundreds or thousands of times. And so the spatial pattern of the glow of light is fully established. When Stephen Jacques from Oregon talks about this being a glow ball of light. So that glow ball is fully established. So that as time goes on here, the only way that glow ball evolves is by being absorbed. So you no longer, nothing about the dynamics of that any longer depends on the scattering, because the shape, the distribution is already established. And all that can happen is that the photons are extinguished by absorption. So it's a beautiful result, and it really is true. This is a measurement done on the muscle, showing that this theory really does fit with the data. So this is measurements made on the muscle of an individual. And so if you do this experiment and you measure this final slope, you have a measurement of the absorption coefficient. So if you do that as a function of wavelength, you have the absolute absorption spectrum. So you can measure how much hemoglobin, how much oxyhemoglobin exactly. So it's really a surprising result.
So if you are far or near the entrance
Yeah.
of light, so that will change the amplitude only, right?
If you're far away, if your detector and the source are closer or further away, it changes, for example, the position of this peak. If you're further away, then the peak will happen later, and of course, the further away you are, this will be smaller. Okay. But it does not change this final slope. So all the curves, if you change the scattering or the distance, these curves are all different here, but they all come to the same final slope. So this is a very important result in biomedical optics. It tells you that you can do absolute spectroscopy even in tissue, which is highly scattering. Now, when these experiments were first done, the technology required to do this was about the size of this room. But now you can get a picosecond diode laser that's, this size. The detectors are still expensive and difficult, but this has become a feasible technology.
But you can do similar to probe, but not exactly. Such a way that instead of having a time for a single pulse, you just suddenly many pulses.
So there's numerous variations on how to do this, but in fact the simplest way is that you do so-called frequency domain, and you measure the phase shift. But the important result spectroscopically is shown here. So I think I'm going to stop there, because now I want to go on to imaging and so on, but maybe I'll stop with that result. Do people feel that they understood that? It's pretty obscure. It's not easy to get your mind around that. Just think about it in terms of the scattering material. The scattering basically spatially spreads the light, and once it's completely spread, then the only thing that can happen is that you remove the photons by absorption.
Can you clarify the reference here? What journal is this?
Oh, actually, this is a very old. This is now. When did we do that? We did that in about 1988 or something. So, yeah, I can give you references on that.
Do you remember the journal?
What journal was that in?
It's okay. Please,
I don't know. Applied Optics or something. I can find it. Yeah. Well, you can find that it's probably on my CV somewhere. Yeah. But anyway, so that was an exciting result, and actually started a whole new field of time-dependent spectroscopy. Okay, so let's leave that for that today. Thank you.